All right. So we're going to look at Edgenuity from Algebra 2, and we're going to look at Section 6.2 and then 6.4. Section 6.2 is called Solving Exponential Equations by Rewriting the Base. The objective is to solve exponential equations by rewriting bases, so that's pretty straightforward. Let's look at a straightforward version of how you might do this. We'll get into more complicated versions of how to do this, but this is a pretty straightforward one. These numbers right here are the base for these exponential expressions here and here. And what happens is, as long as these two bases are the same, what you're able to do is ignore them as long as they're exactly the same, and you can take the exponent parts and set them equal to each other. So I can ignore these 9s because they're both a 9 and say, well, that means that 2x plus 1 equals 3x minus 2. And then I can proceed to solve that. So this would be, I think the most straightforward way to solve this is to subtract 2x on both sides. So I have all my x's on the same side, and that would give me 1 equals 3x minus 2x, which is 1x, or just x, minus 2. And then add 2 to both sides, and have 1 plus 2 is 3, equals, and then negative 2 plus 2 is 0, so I have x plus 0, which is just x, and so I have my answer that x equals 3. I will pause for a moment to let you look at this and see if there are questions. All right, there being no questions, I will move on. Here's another one. Notice the same base again. And then we've got these two things up here that, because the bases are the same, we can just set them equal to each other. So we've got x squared plus 4x plus 4 equals 9x plus 18. So the usual way you want to do this is, because of this x squared, we'd like to have everything on one side, have the whole thing equal to 0. So let's do that by doing minus 9x and minus 9x, and also doing minus 18 and minus 18. That'll give me x squared plus, I've got 4x minus 9x, which is a negative 5x, plus I've got 4 minus 18, which is negative 14, and then everything over here, this subtracts to make 0, this subtracts to make 0, so it all equals 0. And my hope is that I'll be able to factor this, okay? And if I look at it, rewrite it one more time, sometimes these are easier to look at with the minuses in them. So what I would need is two numbers that multiply to make 14 and subtract to make 5. So the setup looks like this. I've got an x and an x. That's how I'm going to make the x squared, is x times x. And then a minus here would mean one of them is going to be plus and one of them is going to be minus. And then I got to find those two numbers that multiply to make this and subtract to make this. That is, multiply to make this number and do this to make that number. And two numbers like that are 7 and 2. 7 times 2 is 14, and 7 minus 2 is 5. And then the bigger number goes with that sign. So 7 here, 2 there, equals 0. Now, you can't always pull off this trick, but it makes the problem a lot easier when you can, because then you can use what's called the zero product property. That is, I multiplied this, and I got 0. So either the first one has to be 0, or the second one has to be 0. And I don't know which, but I know one of them has to be 0. That's the only way I multiply and get 0, is something times 0, or 0 times something. So I'm going to take into account both cases and then solve them both. So for this one, I'd subtract 2 on both sides and get x equals -2. And for this one, I'd add 7 to both sides and get x equals 7. So my two answers are x equals -2 and x equals 7. I'll pause for a moment to see if there are questions. Okay, there being no questions, I'll move on. Now let's talk about what happens when you don't have the same base. Starting off. So it would be nice if I could take that number right there and I could turn it into a power of 7. Okay, so with a little bit of calculator work, I'll do some side work over here. 7 to the first is 7. 7 to the second is 49. 7 to the third. So then I have to start figuring out what 7 to the third is. That's 7 times 7 times 7, or 49 times 7. That's 343. What about 7 to the fourth? That's 343 times another 7. That's 2,401. And hey, look at that, right there. So, since I have 2,401 as a power of 7, I can rewrite it that way. I can put in 7 to the fourth, which, if I calculated it, would come out to 2,401, and have that equal 7 raised to the 6 minus 2x. And then I have the like bases again. And once I have the like bases, I can just set the exponents equal to each other and solve. So I might do -6 on both sides and have -2 equals -2x, divide by -2, divide by -2, and have 1 equals x. And there we are. I'll pause for a moment, let you look at that, see if there are questions. To pause just for another moment so I can change an attendance issue. All right, there being no questions, let's move on. Now, if I wanted to solve this one, if you think about 8, what you'd really love is to have 8 be a power of 4, but 4 to the first is 4. 4 to the second is 16, so 8 is somewhere between these two, and that means that I can't do a straightforward thing like that. So instead, the next strategy is, well, what about changing both of these numbers to be a smaller power, to have a smaller base? For instance, 2 to the second is 4, and 2 to the third happens to be 8. So I could use both of those. I could say, instead of saying 8, call it 2 to the third, and raise that to the negative 2x. And instead of saying 4, I could say 2 to the second, and raise that to the second. This 2 is that 2. And now I am able to do it. I have to do a little bit of simplification first, but I am able to do it. When you raise powers to other powers, like the case here and the case here, you have to multiply those powers. So this is 2 to the 3 times negative 2x equals 2 to the 2 times 2. Whoops, got ahead of myself there. To the 2 times 2, which is 2 to the negative 6x equals 2 to the 4th. And now I've got those like bases and exponents that I can set equal to each other. So now I can just do negative 6x equals 4. I can divide by negative 6 on both sides, giving me that x equals positive divided by a negative is a negative 4 over 6. And that can reduce by 2 to be 2 over 3, so I get an answer of negative 2 over 3. I'll pause for a moment, let you look at that, see if there are questions. Okay, there being no questions, so I will move on. Let's talk about something a little bit different here. Same idea, except for we're going to throw a fraction in right there, and I'll show you how to deal with that. But it's the same idea, okay? We're going to have to rewrite both of them. And what happens is, so 1/4 is the reciprocal of 4. And one way of writing the reciprocal of 4 is 4 to the negative 1 power. So if 64 were a power of 4, that would be really convenient and really nice, right? So 4 to the first is 4. 4 to the second is 16. 4 to the third is 16 times 4, which it turns out is 64. So I'm able to use 4 to the third and 4 to the negative 1. So let's rewrite this. 4 to the third raised to the 1 minus a, that's an a there, equals 4 to the negative 1 raised to the 3a minus 2. And then I have to do the multiplication. That's 4 to the 3 times 1 minus a equals 4 to the negative 1 times 3a minus 2, which I might call, instead of minus a, I might call plus negative a. Instead of minus 2, I might call plus negative 2. That helps me keep track of where my negatives are. Then I need to distribute and distribute. So I've got 4 raised to the 3 plus negative 3a equals 4 raised to the negative 3a plus positive 2. And then I've got the same bases, so I can ignore the bases and set these two things equal to each other. 3 plus negative 3a equals negative 3a plus 2. And let's say I want to get rid of the negative 3a here. I'd add 3a and add 3a. That'll give me 3 equals, but this gives me 0, right? So it's 0 plus 2 is 2. And this is what we call a contradiction. And the symbol, that's the symbol for contradiction. And what just happened here is there's no A that can make this happen. Okay, so this one, it turns out, is no solution. So that can happen from time to time. These problems might be impossible to do. And you just got to be on the lookout for that and be aware that that might happen. Okay? If you get an identity instead of, if instead I would have, say, gotten 3 equals 3, then I would have known that that these are infinite solutions, that there's infinite number of solutions to this. Okay, I see no questions. So moving on to our next problem. What happens if we have some other weird number with this? Well, then what the heck do? We can't just multiply these two. Okay, very important. These are attached and bonded stronger. In other words, this has to happen first. This is collected. Okay? So how do we deal with this? Well, you might divide by 32, but the other thing is, what if I can represent this as a power in the same way? In other words, I know I can represent this as a power of 2. I've already done it. I can represent this 4 as a power of 2. Can I represent the 32 as a power of 2? So let's look at some side work here. I know 2 to the second equals 4. I know 2 to the third equals 8. And then 2 to the fourth is 8 times 2 is 16. I'm just multiplying by another 2 there. And then 2 to the fifth, if I multiply by another 2, is 32. So I can indeed represent the 32 as a power of 2 as well. So let me rewrite it that way. With 32 being 2 to the fifth times 8, we'll call 2 to the third raised to the negative x, equals, instead of 4, we're going to call it 2 to the second raised to the second. And then raising powers to powers means multiplying. So that's 2 to the fifth times 2 to the negative 3x, because 3 times negative x is negative 3x, equals 2 to the fourth. 2 times 2 is 4. Now I've got two things with the same bases being multiplied, and the rule for that is that you add the exponents. So this becomes 2 to the 5 plus negative 3x equals 2 to the fourth. And now, all of a sudden, happily, I can ignore the bases and have 5 plus negative 3x equals 4. And I can do something like subtract 5 on both sides and have negative 3x equals negative 1. Divide by negative 3 on both sides and have x equals, a negative divided by a negative is a positive, and there's no reducing or changing 1 over 3, so I just leave it that way. I'll pause for questions. All right, there being no questions, I will move on. So let's do something even more complicated now, okay? Now we've got this number 243 coming up and the number 9 coming up. So it would be really convenient if 243 was a power of 9. So let's check that first. 9 to the first is 9. 9 to the second is 81. 9 to the third is times another 9. So I'm going to use my calculator on that and say, what's 9 to the third? So 81 times 9 is 729. So this does not help me because I leaped way past 243. Okay, well, if that doesn't help me, I have to explore more options. Well, another option is that 3 to the second I know is 9. So maybe I should explore 3s. 3 to the third is times another 3, that's 27. 3 to the fourth is times another 3, that's 81. 3 to the fifth, so let's do 81 times 3, and that is 243. So that's nice. So let me represent all the 243s as 3 to the fifth power. So we'll have 3 to the fifth raised to the negative y equals 1 over 3 to the fifth, and we'll clean that up a little later, raised to the 3y times 9, which I'm going to call now 3 to the second, raised to the negative 2y power. So now I'm going to do a couple of things. First of all, I'm going to multiply powers on the first one. So 3 to the negative 5y equals 1 over 3 to the fifth. This right here is the reciprocal of 3 to the fifth. So if I just put a negative there, I account for the 1 over. And then I'll have it raised to the 3y, and I'll clean that up in just a second. And then 3 to the 2 times negative 2y is negative 4y. So now I've got 3 to the negative 5y equals 3 to the negative 15y plus negative 4y, because I'm multiplying the same bases, so I add the exponents. So once I have a single exponent for that by multiplying, then I can add the exponents. And that allows me to finally have the same base one time on each side, and so I can ignore it, and have negative 5y equals negative 15y plus negative 4y, and then I can simplify that part and say negative 5y equals negative 19y. That's even nicer there. And then I could do something like maybe I could add 19y to both sides. And that would be 14y equals 0. I could divide by 14, divide by 14, and that would give me y equals 0. And so that would be my answer, y equals 0. I'll pause to see if there are questions. All right, there being no questions, I will move on. And now we're going to move on to section 6.4, evaluating logarithmic expressions. Now, there's a lot more objectives, but this will actually be a much shorter set of examples. So 3 objectives here. We want to evaluate common logarithms using a calculator, evaluate logs by converting between logarithmic and exponential forms, and then solve equations by converting between logarithmic and exponential forms. So the first thing is we got to be able to rewrite things, okay? So when we want to evaluate here, it's almost the same process as the stuff we were doing, but you got to be able to rewrite. And I'm going to show you how to rewrite. Set this logarithm, and the way you read this is log base 3 of 27. So log base 3 of 27. And if I set this equal to some variable, let's say n, I can rewrite it in what's called exponential form. And the way you do that is you make it an exponent. You make it have an exponent. You make it a power. And the way you do that is you take the base and you make it the base of the power. Then you take what it equals and you make that the exponent of the power, and it equals the number right here. So 3 to the n equals 27. And then 3 to the n equals, and 27 is a power of 3. It's 3 to the third, and then I can ignore the 3's, and I get n equals 3. So then I can take this and plug it back up here and say log base 3 of 27 equals 3. Let me do that again with the one down here. I'll set it equal to, let's say, m this time. And I'll rewrite it in exponential form, 5 to the m, a base of 5 to the m, equals 1 over 25. But 25 is just 5 to the second, and 1 over something is the same as that thing to the negative power. So m, because I can ignore the base now, equals negative 2. So then log base 5 of 1 over 25 equals negative 2. I'll pause for questions. Okay, there being no questions, I'll move on. All right, so one of the things that comes up in the lesson is, suppose that the molar concentration for a solution for hydrogen is this. And what they tell you is that you can find the pH balance based on the amount of hydrogen using the equation negative log x and just plugging in where this number is x. And the thing that you really have to know is that log something like this means log base 10 of that thing, and log like that is log base 10 in a calculator. So whenever you see just the log button in a calculator, that is the log base 10. So all you're going to do here is have the negative of log base 10, called the common log, of this big old decimal here. It's got 5 zeros. And you're just going to plug that into a calculator. And you're going to have the negative out in front, and you're just going to put this into the calculator. Okay? So if you're using your phone as a calculator, usually if you turn it sideways, it will turn into a calculator that you can do that with. So you want the log of 0.1234 zeros and a 7 in this case, and that comes out to negative 5.1549, but it'll round to 0.2 because 1.5 rounds to 2. And then we've got negative of a negative, which is a positive. Okay, so that's just putting them into the calculator, and that's, even though this looks like a complicated word problem in the exercises, really it's just putting it into the calculator. I'll pause for questions, let you look at that. Okay, there being no questions, I will move on. Let's talk about solving logarithmic equations now. So if I have this cannot really be solved in exactly this way. I have to rewrite it. And what I'm going to do is I'm going to take the base. Remember, this reads log base 2 of 3x plus 8 equals 5. And if I want to rewrite it in exponent form, that would be a base of 2, and then this becomes the power, equals all that stuff in parentheses. So then this actually becomes a really simple, straightforward problem. I just have to know what 2 to the 5th is. We actually already figured that out earlier today. It was 32. So this is just 32 equals 3x plus 8. I could subtract 8 on both sides. And that would give me what? I think that would give me 24 equals 3x. And then I could divide by 3 on both sides to get the x by itself. And that would give me that x equals 8. And there it is. So, that is one of the simpler versions of problems to solve, but it gives you a good idea of how to solve a problem like this. We've only got one more problem, so I'll pause for questions. And there being no questions, I'll move on. And this is going to be our last problem. Let's say we wanted to solve something with logs on both sides. And all sorts of strange, weird things going on, right? Well, let's look at this separately. These are both log base 10 because it says log and then it doesn't give you a base, and that's how you know it's base 10. Let's let this one equal n. Let's let this one equal m, and then we'll take a look at, actually, I take that back. Let's let it equal n also, because they're both the same, right? So, and then let's rewrite them in exponent form separately. That would be 10 to the n equals x minus 3, and then it would be 10 to the n equals 17 minus 4x. So this equals 10 to the n, this equals 10 to the n, so these are both 10 to the n, which means they equal each other. So I can write them like this, and then I've got something that I can solve, right? So I could add 4x to both sides and have 5x minus 3 equals 17. And I could add 3 to both sides and have 5x equals 30. And then divide by 5 on both sides and have x equals 6. And what you want to do is you want to see what happens if I put 6 in to both of these, okay? So let's plug them back in. Log of 6 minus 3, that's 3, is supposed to equal log of 17 minus 4 times 6, which is 24. Looks like we have a problem there. And that problem is that when I do 17 minus 24, what do I get? Well, I get negative 7. And those certainly are the same, and not only are they not the same, but actually that has no answer at all. So we have to throw this out and say no solution. Now that doesn't mean that every single one will have no solution that come up looking this way. However, you have to bear in mind that it's a possibility and that you have to plug back in and check them. All right, thank you so much. That concludes this